Hello! In this lecture, you will learn about one of the most common uses of hashing, searching for a specific element in an array. The problem of searching is a classical problem in computer science that arises in many situations. For example, each time you log into a system, there's an algorithm in charge of searching for your username. If the search takes too long, you are very likely to give up entering the system. Successful systems really want you to enter quickly. In this lecture, I'm going to show you 3 ways of solving the problem of searching before moving on to how hashing can be used to solve it. In this way, you will have an overview of different approaches for searching. Most probably, you already know some of them. Let's start by defining the problem of searching in the context of this lecture. The input data will be an array of numbers and a number to search for. The algorithm must give as a result the Boolean value true if the number is in the array, and the Boolean value false if the number is not in the array. There is a variant to this problem where the algorithm must give as a result the position of the number. If the number is not in the array, the result is -1. In this topic, we will focus on the algorithm returning Boolean values. True if x is in the array, and false if x is not in the array. Now that we know what the problem to solve is, let's review 4 algorithmic solutions to it. Let's start with solution 1, linear search. Linear search simply consists of checking position by position in the array until you either find the number, in which case the algorithm returns the Boolean value true, or you finish checking each position of the array and the number was not found in any position, in which case the algorithm returns the Boolean value false. This is the pseudocode of linear search. We use this for loop to check the content of each element in the array. If the element is found in one of the positions of the array, the Boolean value true is returned, and the algorithm finishes its execution. If the for loop is finished without having found the element, the Boolean value false is returned. Now, let's have a look at the time complexity of linear search. Let's start with the worst case, that is, the case where the maximum number of operations is performed. This happens when the number is not found in the array. In the worst case, all iterations of the for loop are executed. Therefore, this instruction performs a number of operations linear with n, the size of the array. The verification of this condition is carried out n times. Each time, a constant number of time units is taken. In the worst case, this return is never executed, and finally, this return instruction takes constant time. So, in the worst case, linear search is theta n. In the best case, the number is found in the very first position of the array. In that case, the for loop only performs one iteration and that takes constant time. The verification of the condition of the if statement also takes constant time, and the instruction returning with the Boolean value true also takes a constant time. Thus, in the best case, linear search is theta 1. In terms of memory, linear search only creates a simple variable, the variable I. Therefore, the space complexity of linear search is theta 1. Now, let's move on to solution 2, binary search. Binary search requires that the array is already sorted. In this slide, the value of the number inside each array position is represented in an abstract way by how much each box is filled with the teal color. In this case, we assume that the array is sorted from smallest to largest value, but it can also be the other way around. Binary search starts by checking the middle position of the array. If the element is found in that position, the algorithm returns true and its execution ends. If the element is not found in that position, the algorithm checks whether the number being searched for is lower than or greater than the element stored in the middle position. If the element being searched for has a lower value, for example, then we know it's not necessary to search the right half of the array. So, we discard that half of the array from further consideration and repeat the algorithm in the left half, selecting its middle point. If the element is found in the new middle point, the Boolean value true is returned and the algorithm ends. Otherwise, a new verification is done. Is the number being searched for lower or greater than the element stored in the middle position? If, for example, the element being searched for is greater than the element in the middle position, then we know it's not necessary to search the left half of the array. So, we discard that left half from further consideration and repeat the algorithm in the right half, selecting its middle point. If the element is found in this new middle point, the Boolean value true is returned and the algorithm ends. Otherwise, we know that the value is definitely not in the array. By discarding portions of the array, binary search makes a lower number of comparisons than linear search in the worst case. In this particular case, instead of doing 7 comparisons, that is, checking every single array position, binary search will make only 4 comparisons in the worst case. On the left, you can see the iterative description of binary search using pseudocode, and on the right, the recursive one. Both check on the condition to either continue with the iteration or stop the recursion and perform the same verifications to determine whether the number is in the array or not. Now, you can prove that no matter what the implementation, binary search time complexity is theta log n in the worst case and theta 1 in the best case. In terms of space complexity, both implementations differ. The iterative version only creates a single new variable, mid. Therefore, its space complexity is theta 1. On the other hand, the recursive implementation creates a new variable mid every time a new recursive call is made. As the maximum number of recursive calls is log n, then the space complexity of the recursive implementation is theta log n. So, the complexity of the solutions to the problem of searching that we have looked at so far is summarized in this table. If you want a fast algorithm, you must go for binary search, because its worst-case time complexity is theta log n, much better than the complexity of linear search. Also, because the difficulty of implementing the iterative version of binary search is not high, we would prefer the iterative implementation because it uses less memory space. Now, the question is, can we do better than theta log n when searching for a number? Yes, we can. And that leads us to solution 3. Solution 3 is called direct addressing, and what it does is use the index of an array to represent a number. For example, let's consider the following original array of numbers. A new array is created where each index represents a number. This new array is called bit vector, because it will only store ones and zeros. If the content of the bit vector in position I is 1, then it means that number I is present in the original array. if the content of the array in position I is 0, that is an indication that number I is not present in the array. In this example, the presence of number 8 in the original array is represented by storing a number 1 in position 8 of the bit vector. Instead, all numbers not present in the original array have zeros stored in their corresponding position. Now, searching for a number using the bit vector is really fast. This is the pseudocode of it once you have created the bit vector. You simply access the content of the bit vector in position x. As a result, this searching solution takes constant time to be executed. That is, the time complexity is θ1. However, this fantastic running time comes at the expense of memory. You need to create a bit vector with a size equal to the maximum value stored in the original array plus 1. So, the higher the maximum number in the original array, the more extra memory you need to use direct addressing. For example, in the programming language C, the maximum unsigned integer representable with 32 bits would require a bit vector with 4 billion boxes. Can we get a time complexity as good as direct addressing without using so much memory? Well, under certain conditions, we can. And that leads us, finally, to solution 4, which is based on the idea of hashing. Similar to direct addressing, we will also use an array to store the numbers. This array is called the hash table. When we haven't stored any number yet in the hash table, the table is filled with -1s, or any other number that you know is out of the range of the numbers you will store there. Now, unlike direct addressing, the hash table has a much lower number of elements than the bit vector used in direct addressing. In this example, you can see that instead of having an array with 12 positions to store numbers from 0 to 11, we only have a hash table with 7 positions. The hash table can be any size, but if you know beforehand that you need to store 7 numbers, you make a hash table with exactly 7 numbers, as in this example. Now, we cannot directly store number k in position k as done in direct addressing, because we do not have enough positions to do so. In this example, numbers 8 and 11 could not be represented in the hash table if we used direct addressing. So, what we do now is transform each number into an index in the hash table using a hash function. In this example, we are going to use the hash function h of x equal x modulus 7. So, we apply this function to each number present in the array to determine the position at which they will be stored in the hash table. Let's start with number 8. We apply the hash function to number 8. 8 modulus 7 is equal to 1. So, number 8 is stored in position 1 in the hash table. Applying the same hash function, number 2 goes to position 2, number 11 goes to position 4, number 3 is stored in position 3, number 5 goes to position 5, number 0 is stored in position 0, and finally, number 6 is stored in position 6. Now that the numbers are stored in the hash table, searching for them is really fast. Here, you can see the pseudocode to search for number x in hash table h. We simply apply whichever hash function we are using to the number we are searching. In doing so, we obtain the index where this number should be stored in the hash table. If the number is found there, we return true. Otherwise, we return false. Let's simulate the execution of this pseudocode with this hash table and the hash function h of x equal x modulus 7. Let's assume we are searching for number 11. The search algorithm first calculates the index where number 11 should be stored if it was in the hash table. That is index 4. Next, we check the content of position 4. As position 4 has number 11 stored in it, the condition is true and hence the Boolean value true is returned, signaling that the number has been found. Let's look at a second example with a number that is not present in the hash table, such as number 15. We apply the hash function to number 15. 15 modulus 7 is 1, so the variable index takes the value 1. Now, we check whether number 15 is stored in the position pointed out by the index. No, number 15 is not stored in position 1, so we return false. You can prove that this algorithm has a time complexity equal to theta 1. That is, the time taken to execute the search is constant and it does not depend on the size of the hash table, which is the best we can get. That makes hashing for searching a very good solution, as you can see in this summary table. If you look at the two last rows, you will see that using direct addressing and a hash table have a time complexity of theta 1. However, in terms of memory usage, the use of a hash table is better because the number of elements in the hash table, also called buckets, is much lower than the number of elements of the bit vector used in direct addressing. So, we have seen that using hashing for searching is very efficient. However, we won't always have such a good situation as this. In this case, we knew the numbers that would be stored in the hash table beforehand. In knowing that, we could devise a hash function that was just perfect for this set of numbers. But what happens if you don't know in advance how many and what numbers are going to be stored in your hash table? We will study that case, the problems that arise, and how to solve them in the next lecture.